So in this video, I wanted to run through the heat of neutralisation mandatory experiment. This is on page 205 of your revision books if anyone wants to open that. And the other thing is, I'm going to use 2013's question 3 as an example. So if you want to maybe open that now as well. Okay, so heat of neutralisation is the heat change that occurs when 1 mole of H plus ions from an acid reacts with 1 mole of OH minus ions from a base to make a mole of water. Okay, now the first thing I just want to kind of talk to you about there for 1 second before I start the actual question is that if you're using a strong acid and a strong base, the heat of neutralisation is generally minus 57 kilojoules per mole. Why minus? Because it's an exothermic reaction. When you add an acid to a base, the reaction gives out heat. So that's the negative value. And 57, don't worry about remembering it. They'll ask you it in the question. Now, if they asked you to explain why you would get a lower value than minus 57 kilojoules per mole if you were using a weak acid or a weak base, you might be able to explain, you need to be able to explain that. So what do you know about a weak acid or a weak base? Well, you know they don't fully dissociate, okay? So what you will need, or what the reaction needs to do, is some of the energy that would have been made is used to make the weak acid and weak base dissociate fully. So some of the energy is used to encourage dissociation, and therefore your value at the end for delta H is less than minus 57. So that's what you need to say there if you're asked that in a question, okay? Now, I'm going to go now to the question that you had there, or the one I said I was doing 2013, question 3. The first thing they asked you was to define heat of reaction. Heat of reaction is the heat change when the number of moles of reactant indicated in the balanced equation for the reaction react completely. So heat of reaction is a general definition or a general term that kind of incorporates or encompasses all of the different types of reaction. Then you have a different definition for heat of combustion, heat of formation, heat of neutralisation. Neutralisation, formation, combustion are all different types of reaction. Heat of reaction is your general definition, okay? So really important in this chapter that you know all of those definitions there, because they're going to come up in question 6 as well, even if they don't have, if they don't pick this experiment for question 3. Now, the next thing they asked you then is B, to suggest a suitable material, well, something like polystyrene. You want to use a material or a cup that isn't going to lose heat to the surroundings. So it's a good insulator. So polystyrene is a good insulator. Any heat that you make from the reaction of the acid and the base in the cup needs to stay in the cup so that you can record that temperature rise using the thermometer. Okay, now the next thing they asked you then, was it an advantage of using a burette to measure volume of base? Well, a burette is more accurate than a graduated cylinder for measuring volume. So that's all you have to say there. And a disadvantage. Now, this is a bit of a funny one. Like if you're measuring out, like remember one of the precautions here is that you always have the acid in the cup first and you add the base to the acid. So the acid is down here, you're adding in the base. The reason for that is a safety issue. If there was any splashing or spilling back from the cup, then the base would be less corrosive. So the acid is at the bottom, then you add the base, okay? Now, if you were using a burette to measure base, then do you remember what you have to do now at the start? You have to measure the temperature of the acid and the base separately. So if we take like the actual example that I'm using, 2013, they said that the acid was 13 degrees Celsius and that the base was 15 degrees Celsius at the start, before they were mixed together, okay? Now, one thing to say there maybe is that you would use the same thermometer to measure the acid and the base beforehand. Sometimes the graduations in the thermometers, there can be inaccuracies. So to ensure a more accurate result, you would use the same thermometer, but you must make sure that you rinse the thermometer before you put it into the base, when you're recording the temperature of the base, after it has been in the acid. So rinse it off first with some deionized water. Now, the point being is, right, while you were measuring out the base in the burette, maybe the temperature of the acid in the cup would change. Maybe the temperature of the base in the burette would change. It's too slow. So it's too slow and cumbersome to be using a burette to measure out volumes for this experiment. You can just use a graduated cylinder and it's much faster. Okay. Now, D then says, state 2 ways of ensuring that the rise in temperature was accurate. Now, there's quite a few precautions here that you can take for this experiment. The first thing is that you, as I said, that you use the same thermometer to measure both the acid and the base. The thermometer has to be an accurate thermometer that can read to within at least 0.2, sorry, that shouldn't be there, degrees Celsius. So the ones we used last year would read between 0.1 of a degree, but you need one at least that could read between 0.2 of a degree. Like the ones you would have used in junior cert, the thermometers in junior cert, you could read 11, 12, 13 degrees, but you can't have 11.2, 11.3, whatever. So you need thermometers that are more accurate than that for this. You need to make sure that you stir the solutions, that you add them together without splashing, that you stir the solutions quickly. Stirring the solution would make sure that the heat that's made between the reaction of the acid and the base is distributed completely throughout the solution, so that you wouldn't have a temperature heat spot sort of in one part of the solution and the other bit of the solution is colder, that the heat would be uniformly distributed by stirring. The reason for the lid, of course, is to stop heat escaping through the top of the cup. You don't want heat going out through the top there. The reason for the avoiding the splashing, firstly, it's a safety thing. You don't want the acid or the base splashing on you. But other than that, you know, when you're going to calculate the heat that you made in the cup in a second, you're going to use your formula MC theta. To calculate the mass of the solution, you need the accurate volumes. So if you have solution splashed out of the cup, you don't know what volume you have in the cup then at that point, okay? So they would all be precautions that you would take to ensure that you've got an accurately measured temperature increase. Remember now, there's a difference between heat. Heat's a form of energy. It's measured in joules, okay? Temperature is the degree of hotness. You use a thermometer to measure it, and it's degrees Celsius. So in a minute, we're going to be converting a temperature rise into amount of joules, into heat. Oh, the other thing now, before I go to the calculation actually, is sometimes they might ask you, if they used very dilute solutions of acid and base, okay, you know, would there have been an experimental problem encountered, or whatever way they'll phrase the question? Well, yes, because very dilute solutions of acid and base, you're not really going to make that much heat in the cup. Therefore, the temperature rise is going to be very, very small, and that can be very accurate, or hard, to measure accurately. Okay, so you'll have issues there with accuracy. Now, what am I doing now? Where am I now? Oh, E. Now, they specifically asked me here now to calculate the number of moles of HCl. We would probably have gotten the MC theta last year first, I'd say, as our step one. So we're just going to mix, I'm just going to change it to here. So MC theta then is going to tell me the heat that's made in the cup. So I'll do that afterwards. Now, the formula for number of moles, well, this is a solution, V by M all over 1,000. The volume of acid that they used was 75. It was a 1 molar acid. Divide that by 1,000, and so you're going to get 0.075 moles of acid. So that's my answer A there. How many moles of acid, or how many moles of HCl? Oh, bear in mind as well, it's HCl, right? That would be important, wouldn't it? Monobasic. So you know that 1 mole of HCl makes 1 mole of H plus ions. We'll come back to that again there at the end. Now, MC theta. So M stands for mass, and that has to be in kgs. C stands for the specific heat capacity, and the units for specific heat capacity are joules per Kelvin, per Kelvin. So that's why your mass has to be in kgs, because your unit for specific heat capacity would be in kgs. Those of you doing physics are probably more familiar with specific heat capacity. Chemistry, you don't really need to know much about it. It'll be given to you. It's a constant value that's given to you. But it's essentially the amount of heat that would be needed to increase 1 kilogram of a substance by 1 degree Kelvin, to increase the temperature of a kilogram of a substance by 1 degree Kelvin. Don't worry about it. You'll be given it. Now, what was the temperature rise in this question? The initial, now you have to get the average, don't you? The acid was 13 degrees, the base was 15 degrees, so get an average starting temperature of 14 degrees Celsius. If both solutions are not the same temperature at the beginning, then you get an average. The final temperature then was 20.9, so the difference there is 6.9. Okay, so I'm going to fill all of that in there now in the next slide. So MC theta. Now, the mass. My dear Vera, I don't know the mass, so I cover the mass. So the formula then becomes density times volume. 1 gram per cubic centimetre, they told me in the question that I assume the density is the same as water, so it's 1 gram per cubic centimetre. And the volume, what was the volume of solution in the cup? Well, they put in 75 cubic centimetres of acid and 75 cubic centimetres of base, so that's 150 in total. So my mass is 150 grams when I multiply 150 by 1, density times volume. But you must have it in kgs, lads, so you must divide that, you must divide by 1,000, so you're going to get the mass out at 0.15 kgs. So I'll fill that in over here now, 1.5. Now, my specific heat capacity, they told me, was 4.2 in the question. Now that's kilojoules, so my answer will come out in kilojoules. So watch the unit as well. And the change in temperature we calculated in the previous slide was 6.9. So when I calculate all of that, I'm going to get kilojoules now for the amount of heat that I made in the cup. So that's 4.347 kilojoules of heat made in the cup. Now, How many moles of acid was responsible for making that much heat? That's my next step. You equate your number of moles to the heat that was formed. In the previous, or part 1, step 1, we figured out the number of moles was 0.075. So how much heat would 1 mole give? Divide both sides by 0.075, and then you're going to get minus 57.96 kilojoules per mole, okay? Negative value, lads, always give the heat of neutralisation a negative value. Is that all right? Now, lastly then, bear in mind that this is HCl. So 1 mole of HCl, will give me 1 mole of H plus ions. But if it was sulfuric, say, so imagine that this acid was sulfuric acid, H2SO4, 1 mole of that acid would actually in fact give me 2 moles of H plus ions. So I would have to divide this value by 2 at the end if the acid was sulfuric, because this value here is for 1 mole of sulfuric acid, but how much heat would I get from just 1 mole of H plus ions? I'd have to half it by 2, but it wasn't sulfuric acid in this instance, so that wasn't necessary, okay? Any questions, please ask. Finally then, for part F, it asks you to identify the hazard associated with use of these solutions. Well, that would be your corrosive symbols. Will you familiarise yourself with your safety symbols? And the front copy of your book there, inside the front cover, there's the safety symbols are there. So the corrosive one is where you have the 2 test tubes dripping liquid out of them. Do you remember? And like one is burning a table, the other is burning your hand. So they asked you to draw that there. And then what experimental problem would have been encountered if it was a dilute acid and base? Well, I had that earlier. You would produce very little heat. Therefore, you would see a very slight increase in the thermometer.